Good day to everyone. Today we are here to present our class-produced project in CALENG3 entitled Application of Differential Equations in Real-Life Engineering Problems, specifically on population problem. We are Group 8 and we are composed of Remorca, Santa Maria, and Valdez. The growth of the Earth's population is one of the pressing issues of our time, as our natural resources are depleting. As future engineers, we must calculate the possibilities in population growth in order to develop solutions that will help our environment. We can ask ourselves the following questions. Will the population continue to grow? Will there be a time that population growth may level off? These questions may be answered or addressed through the use of differential equations.
Today, we are going to learn about population problems. As examining the world's population growth may be difficult to do without accurate data, we will be utilizing a simple problem to first understand the concepts in calculating the rate of change in population. First, we use P of t in order to represent a population in a given region at any time t. In order to get its value, we must use the following equation. We use rate of change of P of t equals to the rate at which P of t enters the region minus the rate at which P of t exits the region. Here, the rate of change of P of t is the derivative. For population problems, all the ways for a population to enter the region are included in the entering rate. Birth rate and migration into the region are examples of terms that would go into the rate at which the population enters the region. Likewise, all the ways for a population to leave an area will be included in the exiting rate. Therefore, things like death rate, migration out, and predation are examples of terms that would go into the rate at which the population exits the area. We are given this problem to better learn about the concept of population. A population of insects in a region will grow at a rate that is proportional to their current population. In the absence of any outside factors, the population will triple in 2 weeks' time. On any given day, there is a net migration into the area of 15 insects. 16 are eaten by the local bird population, and 7 die of natural causes. If there are initially 100 insects in the area, will the population survive? If not, when do they die out? We start by looking at the birth rate. We are told that the insects will be born at a rate that is proportional to their current population. This means that the birth rate can be written as Kp, where K is the positive constant that we need to determine. Now, given these, we may develop a differential equation with appropriate conditions. As you can see, we added 15 to Kp as this is the net migration of insects into the area. We also subtract 16 and 7 as these are factors that are reduced from the population. By solving the equation, we then get this. The derivative of p with respect to t is equal to Kp minus 8. We are given the initial conditions p of 0 is equal to 100. This means that there were initially 100 insects. Note that we don't make use of the fact that the population will triple in 2 weeks' time in the absence of outside factors as given in the problem. This means that the only thing we consider is birth rate. With this, the differential equation would become the derivative of p with respect to t equals to Kp.
So, just how does this tripling come into play? Well, we should also note that without knowing k, we will have a difficult time solving the initial value problem completely. We will use the fact that the population triples in 2 weeks' time to help us find k, as the initial number of insects is 100, and in 2 weeks' time, or 14 days, the number will triple to 300 insects. This could be presented as seen below. Given the standard form for solving decomposition and growth problems, it can be broken down into a general solution to solve for the population at any given time. With that, we can start by using the variable separable method, and before integrating both sides of the equation must be rearranged in a way that all similar variables are together on their respective sides. Similar variables are together, the equation can now be integrated. After the integration, solve for p to acquire the solution for the population at any given time. Using the general solution we have obtained, we apply the initial condition c equal to 100 and the second condition. Since e raised to k multiplied by 0 is just 1, we can say that c is equal to initial population, which is 100. As derived from the initial condition, we use this as our particular solution to solve for the population at any given time. Since we are solving for k, we divide both sides by 100, then take the natural log of both sides. This will result to a k of ln of 3 over 14. As we have already obtained the value of k, we go back to the original differential equation. The newly arranged equation can now be derived through the method of linear differential equations. With that, the given equation is linear and variable p as seen in the following standard form. Therefore, let our integrating factor follow the following format. The integrating factor should be in terms of the independent variable t, and solving for the integrating factor would result to ut equal to e raised to negative ln of 3 over 14 times t. We can now solve the differential equation through the general solution and by substituting the integrating factor ut. Going back to the initial condition, we substitute 100 to pt and 0 to t. With that, solving for c, we get 100 minus 112 over ln of 3. So, we can substitute c back into the equation. Now, the exponential has a positive exponent and will go to the plus infinity as t increases. Its coefficient, however, is negative, and so the population will go negative eventually. In order for the population to go negative, it must pass through 0. In other words, eventually, all the insects must die. We may be able to determine when this happens by calculating for t when the population is equal to 0. After solving for the population which is equal to 0, t will be equal to 50.4115 days. The following is the representation of the population of the insects during the time in which they survive.
So in conclusion, throughout the years, differential equations, or calculus as a whole, continues to help in various concepts in the engineering field. It provides accuracy for planning systems and in hypothesizing certain problems that are needed to be solved in order to improve the way of life. Through this example, we were able to model the population of an area based on certain conditions, such as the entering and exiting rate. This may be applied in our real life as we are able to predict the outcomes of the current situation of our population growth. Overall, this will allow us to determine problems and come up with solutions that will benefit the people in the world. Some students say that we barely use mathematics in our daily lives, but if we look very closely, we will be able to notice how it is evident everywhere. Lastly, here are the references used in our presentation. Thank you for watching.